Okay, so this is calculus area between two curves. This is my second video. And in this one, we're going to look at integrating in terms of y and changing from a function of x to a function of y. So this is a continuation of the last video. This is example 4, and this is an example where we want to rewrite in terms of the y variable. But first, let's solve it in terms of the x variable, just to see the choices and decisions we have to make, and then we'll see how changing it to the y variable will benefit us and that we'll get the same answer both times. So it says find the area of the region bound by the following curves. We see that we have y equals x minus 1. That is our linear equation. And then we have y equals plus or minus the square root of 3 minus x. The positive square root is the top half of the function. The negative square root is the bottom half of the function from the x-axis. So if I draw a Riemann rectangle here, I see that the top of the function is x minus 1, and the bottom of the function is the negative square root of 3 minus x. However, if I draw a Riemann rectangle here, I see that the top of the function is the positive square root of 3 minus x, and the bottom of the function is the negative square root of 3 minus x. So because my rectangle has a different top function and bottom function, that means we need more than one integral. And hopefully you can identify that the split will occur here. Everything to the left of this split I will call region 1. Everything to the right of that split I'll call region 2. And that will be my two integrals that I want to solve. So let's clear some of this out. So region 1, region 2, and again, that's because my Riemann rectangles have different top and bottom functions. So region 1 is equal to the integral of x minus 1 minus the negative square root of 3 minus x dx. So we have our region 1 integral, we're just missing the bounds. Region 2 is the integral from the positive square root of 3 minus x, and for the top of the rectangle, minus the bottom of the rectangle, which is negative square root of 3 minus x dx. So our integrals and the functions are set up. Now we just need to solve for when will these functions, what are the bounds for these functions, when do they intersect? So I need to find this intersection point and this intersection point, and this is the end of my integrals. So this kind of looks like it'll be -1. I want to verify that, so I want to set the linear function equal to the negative square root and solve. So x minus 1 is equal to the negative square root of 3 minus x. And now that I've done this to solve a radical equation, I would like to square both sides. So anything squared becomes positive, so the negative goes away, the square eliminates the square root, and we're left with 3 minus x on the right-hand side. Because it's a quadratic, we need to get 0 on one side, so I'm going to move these terms from the right-hand side over to the left. So we get x squared minus x minus 2 equals 0. And now that we have this, we can factor it. X minus 2, x plus 1 equals 0. And that gives us x is equal to 2, or x is equal to -1. Now, x equal to 2 does not intersect this line. We can see that this line does not intersect this line at 2. It intersects the other square root, the positive. So for this system, that means that x equals 2 is an extraneous solution, and we eliminate it. However, x equals -1 makes sense, and that's our lower bound. So now you would want to go through and solve another system. You want to solve for this intersection, which is setting x minus 1 equal to the positive square root of 3 minus x. And you'll get the same two solutions. You'll get x is equal to 2 and x is equal to -1. But this time, this will be the extraneous solution, and this will be the answer we want here. So then we get our upper bound 2. So let's rewrite this on a fresh page. Region 1 is equal to the integral from -1 to 2 of x minus 1, subtract the negative square root of 3 minus x dx. Region 2, if we go back, we see that that's going to start from x equals 2. And it's going to go to this intersection point x equals 3. You can verify that by setting this equal to 0, set the y equal to 0, and 0 equals the square root of 3 minus x. That means that x must be 3 to get 0. And our bounds for region 2 are from 2 to 3. It's important to always check it algebraically. There have been very few problems from the textbooks that have made it look like it's an integer, but it ends up being, instead of 3, ends up being the square root of 3, or 2 times the square root of 3, or something very close to it, that it looks like an integer answer, but it ends up being something different. So from 2 to 3, and this time it's going to be the positive square root of 3 minus x minus the negative square root of 3 minus x dx. And we have our two regions set up with their individual integrals. We can simplify these a little bit. This double negative becomes a positive. Becomes a positive on region 2 also, so this becomes 2 radical 3 minus x dx. So these are our simplified integrals that we have to evaluate. And this is power rule. And hopefully you identified that you need U substitution for the radical 3 minus x. So R1 is equal to 1/2 x squared minus x from 2 to -1 plus the integral from -1 to 2 of radical 3 minus x dx. So this is the antiderivative for the first part, but now I need to use U substitution for the second part. Let u equal 3 minus x, then du is equal to -1 dx. We need to make this dx negative for the du to interchange with it. And since I changed that, I need to balance it on the outside, because -1 times -1 is +1, and we really didn't change the integral. The other thing we'd have to do is, once we change to u, these bounds only apply to x. So if I plug -1 in for x, then u is equal to 3 minus -1. U is equal to 4 becomes the new bottom bound. And if I plug this 2 in for x into that same expression, 3 minus 2 is 1, 1 becomes the new upper bound. So we have R1 equals 1/2 x squared minus x from 2 to -1 plus the antiderivative. We're changing the bounds from 4 to 1, and it becomes 3 minus x is being replaced with u, so this becomes u to the 1/2. Negative dx is being replaced with du, and then my negative out in front changes this plus into a minus. So now we can write that region 1 is equal to 1/2 x squared minus x with the bounds from -1 to 2. The antiderivative here of u to the 1/2 is going to be u to the 3/2. When you divide by 3/2, you get 2/3. We have a minus out in front here, and the bounds of integration here are 1 to 4. So, as we continue to evaluate now using the fundamental theorem of calculus, so this is f of b minus f of a from the first antiderivative. Then we have minus 2/3, 1 to the 3/2 power, minus 2/3, 4 to the 3/2 power. We need a new slide to continue here. So R1 is 1/2 times 4 minus 2 minus -1 squared is 1, so it's 1/2 minus a negative becomes plus 1. This is the first antiderivative minus the second antiderivative is 2/3 times 1 minus 2/3. 4 to the 3/2 power is saying the square root of 4 cubed, which is 2 cubed, which is 8. So 2/3 times 8. So we have 1/2 of 4 is 2. 2 minus 2 is 0. Minus 1/2 plus 1 is 3/2. So that's -3/2 we have here. Minus 2/3 minus 16/3. R1 is -3/2. 2 minus 16 is -14/3. The double negative makes it plus 14/3. -9/6 plus 28/6 gives us a region 1 area of 19/6. Okay, so then we go back and we say, well, let's solve for region 2. And you will use U substitution for this one again. U is equal to 3 minus x. Du is equal to negative dx. I'm going to move the 2 out front, -2 u to the 1/2 du. If we plug these bounds in to get new bounds, 3 minus 2 is 1 on the bottom, 3 minus 3 is 0 on top. R2 is -2 times, the antiderivative is 2/3 u to the 3/2, 0 to 1. R2 is -2 times 0 minus -2 times 2/3 times 1 to the 3/2. So -2 times 0 is 0. And we're left with negative of -4/3. So R2 is equal to +4/3. And again, we said that anytime we are working with area between two curves, we expect our answers to be positive. We have two positives for our two regions. Now the total area is region 1 plus region 2, which is equal to 19/6 plus, this becomes 8/6, which is 27/6, which if we reduce that is 9/2 or 4.5. And that's the answer to the area for the region you see here. And we solve that by using x variables. Now we could rewrite this and do this problem again using y variables. And you'll see the benefit to doing that will be we can do this with only one integral. So the first thing we want to do is change our functions to functions of y. change to functions of y. So if y is equal to x minus 1, then x is equal to y minus 1. That's a function of y. If y is equal to plus or minus the square root of 3 minus x, if I square both sides, I get y squared equals 3 minus x. And I'm going to switch things around, move x to the left and y squared to the right. And it's a function of y. And this is a sideways parabola. So the benefit here is that this function doesn't need two functions like it did with x. I don't need a positive and negative square root. That function is 3 minus y squared. And this function is y minus 1. And when we draw our rectangles, we draw them sideways now because it's a function of y. Because instead of dx, we're integrating with dy or delta y. Now, with functions of x, we do top minus bottom, but with functions of y, we do right minus left. So function of y, area between two curves, is right function minus left function. And this should make sense because when you do top minus bottom, the top is where y is positive and the bottom is where y is negative. So you do positive minus a negative and you get a positive result for area between two curves. Well, with functions of y, if you take the right side, that's where the x-axis is positive. And if you take the left side, that's where the x-axis is negative. So positive minus a negative gives us that double negative and we get a positive result. So sideways rectangles, delta y, that means our functions have to be in terms of y, and we do right minus left. Integrating functions of y, use horizontal, Riemann rectangle, and that means the height of the rectangle is delta y, or we can say the width of the rectangle. And the length of the rectangle is equal to f of y minus g of y, or we say the right minus the left. So let's solve this problem now as a function of y. And we'll see that we only need one integral. How do we check how many integrals we need? Well, I tell you, draw Riemann rectangles in different positions of the shaded region to determine if there's a change. So if I draw a Riemann rectangle here, the right function is f of y equals 3 minus y squared, no matter where I draw that. And the right function is g of y equals y plus 1. If I draw the Riemann rectangle anywhere, it's those same two functions. So if it's always the same two functions, that means one integral is needed. And we can now say that the area between these two curves is the right function, 3 minus y squared, minus the left function, y plus 1, dy, because we're using horizontal rectangles. And now we need to look at the y-axis for the lowest and the highest points of the shaded region, because we're now dealing with y variables. And if we set 3 minus y squared equal to y plus 1, we'll get 0 equals y squared plus y minus 2. 0 equals y plus 2 times y minus 1. Y is equal to negative 2, and y is equal to positive 1. Those are our bounds of integration. Area is equal to the integral from negative 2 to 1 of negative y squared minus y plus 2 dy. This is the simplified integral. We just took the polynomials and joined them together. And what you should notice here, power rule for integration. No u substitution needed. So the benefits that came are we only needed one integral, and this is simple power rule. When we were solving it in terms of x, we needed two integrals, and we had to use u substitution twice. So I'm going to take this onto another page so that we can work it out. And now when we find the antiderivative, we have negative 1/3 y cubed minus 1/2 y squared plus 2y from 1 to negative 2. Negative 1/3, 1 to the third power, minus 1/2, 1 to the second power, plus 2 times 1. This is the f of b of the fundamental theorem of calculus. Now we have to subtract the f of a. You should notice that in my videos, I am constantly using brackets and parentheses to keep my f of b and my f of a separate and organized. That's where many of the mistakes originate. Again, I kept my entire f of b in its brackets. I still have to simplify. That's because I don't want to lose the effect of this negative distributing through the right-hand side. Negative 2 cubed is negative 8 times negative 1/3 is positive 8/3. We have here 4 times negative 1/2, so it's minus 2, and then minus 4. And you can work this out and verify that all of this becomes 9/2 or 4.5. Okay, so that is example 4. It is worked out two ways. Shows us the conversion from x to y. And we also got to focus on using horizontal rectangles from the Riemann sums and how they define our integrals in terms of y and how we subtract the right function, or we take the right function and subtract the left function from it. Okay? Watch the video, take notes, practice doing these by hand. College calculus courses are almost all exclusively non-calculator. So practice doing these by hand. Give yourself a head start over the other students in the class going into college calculus courses. The calculator is something you can use for homework, but not for in-class tests. You want to work this out, develop the patience and the thoroughness to do these correctly. All right? Send me questions if you have them, or request a Google Meet and we can set up a session.